These two lectures are going to be about support vector machines. In this first part, I'm going to explain the general idea of support vector machines as a maximum margin classifier, what are support vectors, and how we can solve this problem of finding the discriminant that maximizes the margin with a support vector machine. So we're going to start with this notion, maximum margin classifier, which we can look at this example that we saw previously, where we have different gene activities and we are separating tumor cells from normal cells, and we want to find the discriminant separating these two classes. So we saw our first approach of trying to minimize the quadratic error as measured in the distance between the discriminant and the points, and this didn't work because then these points that are far away start pulling the discriminant out of the position where it should be, and this gives us the intuition that what really matters for this classification are the points that are here close to the other class. Points that are on the right side, on the correct side, and far away from the discriminant are not really important because they are trivial to classify once we put the discriminant in the correct position. So we use logistic regression, where we are minimizing this logistic loss, and we are using the sigmoid function, this function here, so that the function, as this function becomes nearly constant as we go away from the discriminant, the points that are far away do not have a greater weight and do not influence the position of the discriminant. So when we're trying to fit with this regression the probability of belonging to one of the two classes, we will end up finding a frontier here between a discriminant here at the interface between the two classes, because that is the way to minimize this logistic loss by adjusting one of the parts to class 1 and the other part of the function to class 0. So this is the result that we can get with logistic regression. But one thing that we find is that if we have a very steep function here in this logistic function, we will have a larger range of possible values where the error is nearly the same, because since the function steps very quickly from 0 to 1, whether we put it more to this side or this side, the error we're going to measure on the actual points of class 0 and class 1 will be the same. So this means that we have some leeway, some looseness in the position of where the frontier is going to be placed, and we saw that this can exacerbate problems with overfitting, because now the frontier may be placed very close to one point, and we saw how we could, with regularization, help solve a bit this problem. So what we can do with regularization in logistic regression, since we have this function here, this sigmoid function, if we force these parameters w to be smaller, the function will increase from 0 to 1 at a lower rate, so the inclination here will not be as strong. So what we can do here with regularization, we force these parameters to be smaller, and we force the change from 0 to 1 to be more gradual, and this in turn will force the discriminant, which we consider to be the midpoint between probability 0 and probability 1, so when the probability is 1/2 of belonging to either class, this will force the midpoint to converge to a position here that is farther from the points in either of the classes. So this is one way where we can force the margin, so this distance between the discriminant and the closest points, to be as large as possible. In the case of logistic regression, we do this indirectly by changing the cost function. We had here the logistic loss function initially, but now we add a penalty that is the sum of all the squares of the coefficients that we are using, adjusted by some constant. So we can multiply by lambda, or using the way it's normally used in the interface in scikit-learn. So this convention, we use a C value and we divide the regularization term by this C value. So the higher the C, the weaker the regularization. But this is a bit indirectly, because we are just changing the way the model is trained and changing the loss function to try to encourage it to produce a discriminant that is more distant from the points. But the general idea here of a maximum margin classifier is to maximize this distance between the discriminant, where we separate the classes, and the points that are closest to the discriminant. So in general, a margin classifier is one in which we can measure this distance. We can measure the distance between the discriminant and the points. And a maximum margin classifier is one that tries to maximize the distance to the nearest points. So we can see here in this diagram, this would be the discriminant, where we separate the two classes. The distance to the nearest points would be the margin, and a maximum margin classifier will move the discriminant so that it maximizes the distance to the nearest points. It will end up being halfway between the closest points of different classes, because that is the way to maximize the distance from the discriminant to the points. We call support vectors all of these points that lie at this closest distance. So the margin is determined by the points that are nearest to the discriminant, and in this case there are 3 points that are nearest to the discriminant, and these would be the support vectors. We call them support vectors because you can imagine that if we throw away all the other points, we would still have the discriminant in this same place, because these are the 3 points in this data set that determine where we must put the discriminant. The others, as long as they are on the correct side over here or over here for the blue class, they do not matter. They do not have an impact on where we should draw the line. So this is the basic idea behind the support vector machine. We want to identify the support vectors and maximize the distance between the discriminant and those support vectors, because the support vectors are the one that will lie closest to the discriminant. And this is, since this distance is the margin, what we're trying to do is maximizing the margin. So let's try to implement this maximum margin classifier starting with this expression for the discriminant. So remember that we are doing the inner product of this vector that is perpendicular to the discriminant. So there is a perpendicular vector here that describes the orientation of this line. We multiply by each example, and then we add this additional parameter, this constant, that will determine if this line is more up or down along this axis. So this will give us a value that can either be positive or negative, and it will be positive on the side of class 1, negative on the side of class -1, for example. We can consider the distance to the hyperplane separating the classes, the discriminant, if we divide this value by the size of this vector. So this will normalize and we'll actually get the distance in the units of the coordinates. Because remember that this discriminant must be defined by a vector that is perpendicular, but this vector can be larger or smaller. So the value here can grow faster or slower depending on the value of w. But if we divide by the length of this vector, so the norm of the vector, we normalize this, and now we have a value that is a signed distance. It gives us the distance to the discriminant with this expression, but it has a positive sign on the side of class 1 and a negative sign on the side of class 0, or class -1 if we want. So let's consider that we have these class labels, -1 and 1. We multiply each of these by the signed distance. And so if the points are correctly classified, they are on the right position, a class -1 multiplied by a negative sign distance will give us a positive value, and the class 1 multiplied by a positive sign distance will also give us a positive value. This scaling factor means that we will always have a distance measure here, regardless of whether this vector is larger or smaller. But now what we want to do is to optimize these parameters so that the smallest value of this sign distance is as large as possible, because the smallest values of this sign distance correspond to the points that are closest to the margin. And we want to adjust the parameters of our model so that the closest points are as far away as possible. So we're going to maximize the minimum distance to the margin. Okay, this is very simple to implement because we can just write down this expression here. Basically, we need to reshape we may need to reshape the matrix, but we do this inner product of all our data and the coefficients for the vector, which is this part here. And then we add the constant term there, the last parameter. Now we divide by the norm of the coefficients. So this is basically the square root of the sum of the squares of all the parameters in this vector, so to normalize, and we multiply by the class labels. So we can do this, we multiply by the class labels, divide by the norm, and now we want to find the minimum of these distances and maximize that minimum. So this function gives us the minimum. We want to maximize. We have a minimize function in SciPy, so we can do this easily just by changing the sign there. So the reason to change the sign here is because instead of having a maximization function, we are using a minimization function, but the idea is the same. We want to find the value for our coefficients, for our parameters of the model, that will maximize the smallest distance to the discriminant. So we can, in a few lines of code, implement this, run minimization, and look at the result, and it doesn't work. So if you run this several times, this will give you complete nonsense results, and because this minimization function simply cannot find the optimum value. And the reason for this is that remember, when we talked about minimization, we are sliding down the gradients of a function until we find the minimum. But as we keep changing these parameters, the line here will change orientation and the closest points will start to be different points. So if the line is like this, then these are the closest points. But if we change the inclination of the line, then other points here may become closer and so forth. And as we change this, we create discontinuities in the derivative. So if we look at the loss function that we're trying to maximize here, this would be the smallest distance between the closest points and the discriminant, and we want to find the maximum of this. So a set of parameters in our model that maximizes the distance to the closest points. But since the closest points keep changing, this function has discontinuous derivatives. So when we are trying to reach the optimal points here, the derivatives will change from one iteration to the other discontinuously, and this will make it impossible for the minimization algorithm to find, or the maximization algorithm to find, the correct solution. So the problem here is that although we can express the problem very simply, we cannot solve it with the usual optimization methods because the derivative is discontinuous and we cannot find the optimum value. So this is why we need to go around and transform the representation of the problem in order to be able to solve it. And this is what leads us to a support vector machine. So this is the basic idea. We're going to try to maximize the margin, that is, find the parameters for our model that make the distance between the closest points and the discriminant as large as possible. The problem with this is that as we change the parameters of our model, the closest points change, and so there are discontinuities in the derivatives of this target function that we're trying to maximize. So the solution will now involve lots of equations. There are some steps that I'm going to skip, but the final expression is important because where we reach and the way we formulate the problem of a support vector machine will now have some implications on the properties of these classifiers. So I don't want you to try to memorize all of these derivations and the equations, but to understand why we need to solve this in this particular way, and then understand the expression that we get when we formulate the problem of the support vector machine. So we use this normalized distance, this value here, which is the value that we get when we multiply the vector and the examples, the vector that determines the discriminant and the examples. This is negative on one side, positive on the other. If we divide by the norm of this vector, we rescale everything, so we get a distance that has a positive sign on one side and negative on the other. If we multiply by the class, then we know that this will always be positive. So if the class is -1 and this value is negative, this will be positive. If the class is +1, then this should be positive and the result would be positive too. And we also know that since we are normalizing this by the norm of the vector, if we rescale everything, that is, if we change the size of the vector and the constant there, we can still get exactly the same value because we are just multiplying here on the numerator and the denominator of the fraction, so we get the same thing. So let's impose a constraint such that we want for all the points to have this expression at least 1. So it means that the distance, the sign distance between the point and the discriminant is always at least 1 unit. And this is not the normalized one, so this is only the part here on top. And we can achieve this by increasing the size of the parameters if we need. So this will just increase the magnitude here. As long as all the points are on the correct side, we can do this just by manipulating the size of this W. Of course, we can do this trivially, even if the margin is very close to the points, by simply having very large values for W. So now what we're going to do to maximize the margin is to, subject to this constraint, guaranteeing that there is always a value of 1 at least for all the examples that we have for this expression, we want to minimize the size of the vectors we are using here as much as possible. Because if we shrink the size of these vectors while keeping this value greater or equal to 1, we force the discriminant to move away from the closest points so that it can fulfill this condition. So the idea here is that instead of trying to solve that maximum of the smallest distance problem, which has this very difficult problem that it creates discontinuous derivatives, we subject everything to this constraint here. So it means that for all the points we have the product of this expression and the class of the point will be at least 1, and then we just try to minimize the size of the vector. So it would be something similar to what we were trying to do with logistic regression when we added a penalty for the size of the vector, so that the loss function would encourage the use of shorter vectors. But here we are going to explicitly minimize the size of the vector, imposing at the same time this constraint so that we guarantee that we have points at least this value 1 away from the margin. Okay, so now we reduced our problem to a constraint optimization problem where we need to find the minimum for this function subject to that constraint. And this type of problems where we have an optimization problem and constraints can be solved with this method of Lagrange multipliers. I'm going to explain this briefly because the Lagrange multipliers will then appear on the support vector machine, and it's important to understand where they come from. So let's consider this very simple example. We want to find the maximum of this surface here, which is 1 minus x squared y squared. So this would be this parabolic surface here, and we want to find the point where this surface has a maximum, but subject to this constraint. X minus y minus 1 is 0, or x minus y equals 1. So it means this line here on the diagonal, if we have x and y here on the coordinates. So we want the maximum of this surface along this line here, so that would be the maximum here of this curve. To solve this, we can consider that when we reach the maximum along this line, that means that the gradient of the function we are trying to maximize in this direction is going to be 0. So it means we have reached a point that is parallel to the contour line of the function we are trying to optimize, because at that point the function no longer increases or decreases in this direction, and that is the definition of a contour line. It's the line along which the function does not increase or decrease. So when we reach the point here, the gradient must be perpendicular to the line, because it cannot have a non-zero gradient along the line, since we are at the maximum. So if we write an expression like this, some function equal to 0, this will define a contour line of function g, because it is a line where the value of the function is constant. And if this other function is maximum at this constraint, then the two contour lines are parallel. And so the gradients will be parallel too, because the gradients must be perpendicular to the contour lines. Actually, they can be parallel or anti-parallel, but they must be along the same direction here. So what we can do to solve this problem, where we want to maximize some function f subject to the constraint that g is equal to 0, is to create this Lagrangian expression where we use the function f that we're trying to maximize, and this multiplier alpha multiplied by the condition that we have here, so this function that we set to 0. And this Lagrangian, if we now compute the points of this Lagrangian where the derivatives are all 0, we find the critical points where our maximum can be. So the idea is that when we find the derivative with respect to alpha and to x, y of this expression here, we will find points such as this one here, where the derivative along this direction is 0, and we find the maximum of the target function. So let's see, solving in this particular case, we have this Lagrangian, which is the function we are trying to optimize, and the one that describes the constraint, the g that we equal to 0 to describe the constraint, which is multiplied by the Lagrangian multiplier. We want this derivative, the derivative of this expression, to be 0, so now we can compute the derivative of the Lagrangian with respect to x, to y, and to alpha, and now we can solve these equations to get the values of x and y that match this expression equals 0, this one equals 0, and this one equals 0. So this value, 0.5 in x and minus 0.5 in y, would be a critical point of the Lagrangian, which would be a candidate for finding the maximum. It's not guaranteed that all the critical points are maximum. They can be minima, they can be saddle points, but this way we can find which are the critical points and then pick the one that corresponds to what we want. Okay, so this is the general idea where we solve a constrained optimization problem, where we have a function that we want to optimize, this one in red here. We have a function that expresses the constraint, so something equal to 0. And now we write the Lagrangian using the Lagrangian multiplier for the constraint, and we compute the points where all the derivatives are 0. And these are the candidate points for the optima we are trying to find. So let's go back to the problem that we have here. We are trying to minimize this function, so trying to find the shortest vector possible, subject to all of these constraints, which is that the product of the class and the points multiplied by our parameters here, the vector of the discriminant and this constant, must give us a value of at least 1. We can convert this to small or equal to 0, and this gives us a similar solution to what we had here. And now we can write down the Lagrangian, which is the function we want to optimize, which is this one here, and then Lagrangian multiplier multiplied by all these expressions that we have here. So here we can just put the sign there on the outside and do this manipulation, but basically we have a sum over all the points in our training set, because each point in our training set provides one constraint for the problem we're trying to optimize, and now we have for each point in our training set one Lagrangian multiplier, and we include this expression in the Lagrangian, and now we solve to find the critical points where the derivatives with respect to the parameters of our model and to the alphas are all 0. So the derivatives with respect to the vector with the orientation of the discriminant being set to 0 will be equivalent to this. So the vector will be the sum of all the alphas multiplied by the classes multiplied by the points. If we do this, we can compute the vector for the orientation of the discriminant at these critical points. This is what we get for the constant there, the one that we have to add here. This is just a sum that we can find. So when the derivative here is 0, this expression will be 0. The sum of all the alphas and all the class points will be 0 too. And now we can find this optimization. We have this particular representation here. And by doing this replacement and finding the dual problem, I'm going to skip this part. So basically we can replace these expressions for the W and for the W0 where the derivatives are 0. So the W0 will give us this additional constraint. The W can be replaced by this expression. But if we do these substitutions here and then look at the dual representation of the problem, and a dual representation is basically another way of representing the problem that gives us the same solutions when we are doing the optimization. So this is a bit of a complex mathematical set of steps here that I'm going to skip because they are not important for our purposes. What is important for our purposes is that when we solve this with the Lagrangian multipliers and substituting for when the derivatives are 0 and looking at the dual problem, we get this representation of the problem. That is, we want to maximize this expression, find the alphas that maximize this expression. And this is the sum of all the alphas minus 1/2 this double sum of all the pairs of alphas, the pairs of corresponding classes of points, and the inner products between those 2 points. So we're going to do this for all the examples that we have in the training set, and we're going to look at all the pairs of examples. We're going to compute the inner product of those vectors with the features for those examples, multiply by their classes and by the alphas. And we are going to try to find the alphas that maximize this, subject to these 2 constraints. This one came from the derivative here with respect to the W0. So the sum of all the alphas multiplied by the class labels, which can be 1 or -1, must be 0. That means that when we increase the alpha on one class, we must increase alphas on the other class too, so that this balances out. And all the alphas are greater or equal to 0 because this is the basic assumption of the Lagrangian multipliers. They are all equal or greater to 0. So this is the problem that we're now going to solve. And the intuition for this is that if we have points that are surrounded by neighbors of the same class, then this product will be positive, and because they have the same class, either 1 or -1. So all of this will give us a positive contribution for those points that are in the same class. And so we want points that are surrounded by neighbors in the same class to have alphas as small as possible so that we can maximize this expression. Remember that here in these products we are subtracting, so we are penalizing if we increase the size of the alpha for points that are surrounded by neighbors of the same class. If we have points that are near neighbors of the other class, then this product, when we compare the points of different classes, this product will be negative. Since these are neighbors, the inner product of the vectors will tend to be larger and positive. So this will tend to be a negative contribution. And as we have a negative sign here, when we have points that have neighbors nearby that are of the other class, the alpha will tend to grow because we have a positive contribution here, and we also want to maximize the sum of the alphas. Of course, if we increase the value of an alpha of a point in one class, we also need to increase the value of the alpha of some points on the other class, because this must be balanced. And so we have this trade-off where we cannot increase too much one class without increasing also the other. So basically what this optimization problem is intuitively is that as we're trying to fit the alpha, we will tend to bring alphas close to 0 for points that are surrounded by neighbors of the same class, and alphas that are above 0 for points that are near the frontier between the classes. And this is a problem that we can solve with quadratic programming methods, because it has this optimization here subject to these types of constraints, and we can actually implement a support vector machine easily with the optimized function in SciPy. So this, you're not going to do this in practice. In practice, we're going to use the support vector machine class in scikit-learn because it's optimized, it runs faster, and it has a lot more stability, numerical stability. But this is just to illustrate how these things work. So we can start by computing this age matrix, which is just the products, the inner products of all pairs of examples in the training set, multiplied by their respective class labels, which can be -1 or 1. So we can compute this age matrix easily by creating a matrix and now looping through all the points and just placing at each cell on the matrix the dot product of the examples multiplied by the classes here. So in this gives us this age matrix for this part of the expression. And now we also have these constraints here that we need to include, and we need to write the function we want to optimize. So the function is we want to maximize this expression here, since we are going to compute the minimization. Because we have a minimize function in SciPy optimize, then we are going to change the sign here. So this one becomes positive, and this would be the dot product of all the alphas multiplied by the dot product of the alphas and the age matrix. So we can do it like this in 2 steps, and all these sums will be automatically made because we are using matrix multiplication here. And if you recall the rules for algebra, doing these inner products will add up all of these multiplications here. So we multiply this by 0.5, which is this 1/2, and this has a positive sign. And we subtract this part here, this expression here, which is just the sum of the alphas. And this is just because we want to maximize, but we're going to use a minimize function, so we invert the sign of the loss function. This is the vector of derivatives, or the matrix of derivatives here. No, it's a vector of derivatives with respect to alphas that we are going to compute to improve convergence in this case. So usually these optimization methods work best if you can give an expression for the derivatives at each point. But this is just the derivative of this expression here with regards to alphas, which in this term is just 1s, because all the alphas appear multiplied by 1. And in this term here would be the alphas multiplied by the age matrix, these products here that we pre-computed. Okay, so now we put this, load our data. This is the X and the Y data, and we get from the Y's values. We use the class labels. So this, let's assume this is a matrix, and so we need to use the first column to put this in a vector. So this would be for the constraints that we have here. We want all the alphas to be at least 0, and we want the sum of the alphas multiplied by the classes to be 0. So we can add these constraints to our solver like this, which is the dot product of all the classes and the alphas must be 0. So this dot product is the sum of all the products element by element, and the alphas themselves also must be, the derivative of this constraint here is given simply by the class labels, because it's what we are multiplying with the alphas. But this is just to add here to the minimization function, because it needs to have not only the loss function, the target function that we're trying to optimize, this one here, the Jacobian of that function, that is the derivatives, so that it can improve the convergence there and improve the calculation. If we don't supply this, then we'll probably have some problems converging, because it will try to estimate the derivatives numerically, and that is more problematic. And then the same thing for the constraints. So we need to add the constraints and the derivative for the function, this function here that specifies the constraint. And the bounds for our alphas will be between 0 and none, because all the alphas must be at least 0, but they do not have an upper limit. So we can solve this with respect to the alphas using these bounds. And since there is one alpha for each point in our data set, we multiply this by the number of points in the data set. So we start with a set of tuples like this, 0, none, for all of our alphas, and this will be the bounds that we give here to the minimization. Okay, so this is just the setup so that we can find the maximum of this expression here, subject to these constraints. And now we can check the result and look at the vectors where our alphas, this X is the solution here for the minimization, but this corresponds to the alphas. And we're going to look at where the alphas are significantly above 0. So we are not going to compare exactly with 0, because there is always some numerical rounding errors here, but we're going to see those that are above 1 part in 1000 or 0.01, and we see that we have these here, 3 true values in this array. And this corresponds to these 3 points in our data set. So everything else got an alpha that is practically 0. These 3 points got values of alpha that are above 0. So now we can compute the W. We know that the W is the sum of the alpha multiplied by the class and the vector of each point. We can do this. So basically, it's a weighted average of all the points we have multiplied by the class and the corresponding alpha. Of course, since most of the alphas are 0 or practically 0, we can use only the support vectors, and we can compute the discriminant that separates the classes from the support vectors. At the support vector, so at the values where the margin is 1, we can we know this expression here will be 1 for these support vectors. Note that it will be larger than this for the other points, which are not support vectors. But since we know this expression is 1 for the support vectors, which are the ones closest to the margin, we can also compute W0 from there. So using the support vectors, we can get the coefficients, and then we can draw the line here from those coefficients. So this is how we could implement a support vector machine. And what we have is, we started with that particular problem we wanted to maximize the margin, but we could not solve numerically just the problem of finding the set of parameters that maximizes the distance between the closest points and the margin, because as the closest points change, the derivative becomes discontinuous and we cannot solve the problem like this. So we rewrote the problem, the support vector machine, in order to maximize for the alphas, where the alphas are the Lagrangian multipliers we get by imposing that minimum margin condition for all the points. So if we specify that all the points must be at that, have that margin of 1 at least, then this creates one constraint for each point in the training set. This results in one alpha, one Lagrangian multiplier for each point in the training set. So now we solve this. We also can compute these metrics just with the inner products of our points. We are going to see why this separation is significant in the next lecture. But now when we solve the optimization problem, we obtain the support vectors, which are those for which alpha is not 0, and these determine the frontier between the two classes. So you can read a bit more about this on these sections of Alpaidan's book and this section of Marsland. And on the next lecture, we are going to see why this particular solution to the problem, which so far seems to be only just to create a linear classifier, but why this gives us a very powerful formulation that we can extend now to higher dimensions implicitly.